Right now. Recording in progress. Okay, so welcome everybody to today's PRIISM seminar. We're delighted to welcome Professor Sam Pimentel. I'll introduce Sam in a second, but just first thing is two quick notes. One is just please remember to keep yourself on mute during the talk unless you'd like to unmute yourself and ask a question. Speaking of questions, usually what we do is if you have a question, this is for folks on Zoom primarily, feel free to unmute yourself if it's kind of like a short clarifying question. Otherwise, maybe substantive, more kind of lengthy questions, better to hold off until the end. If you prefer to ask a question in the chat, just do so, and I will wait for the appropriate time and ask it out loud on your behalf. Folks in the room, just raise your hand and we'll do it that way. So with that, I'll introduce our speaker. So like I said, we're delighted today to welcome Professor Sam Pimentel from Berkeley. Sam is an assistant professor in the stats department at UC Berkeley. His research aims at understanding causal relationships using large administrative data sets from the medical and social sciences. He develops new ways to form compelling matched or weighted comparison groups in these data sets using tools from optimization. Dr. Pimentel also studies methods for transparent and interpretable inference about causal effects when unobserved confounding variables may be present. He is broadly interested in substantive problems relating to people and institutions, and his methodological work is motivated by collaborations to address such problems in health services, research, epidemiology, and education. Take it away, Sam.
Great, thanks so much for the invitation and chance to be here. I'm excited to share some of my work. What I'll be talking about today is a joint a collaboration with two former Berkeley graduate students, Melody Huang, who's now at Harvard and will be joining Yale as an assistant professor in the fall, and Dan Soriano, who's now at Novartis. I'd also like to thank the NSF for generous support. And I have a link to our archive preprint here if you're the kind of person who likes to follow along with the paper and read all the nitty-gritty technical details. So this is mostly a methods talk, but I want to start by talking about the running data example, just to keep things as concrete as possible. So in 2016, the Colombian government reached a peace agreement with the Revolutionary Armed Forces of Colombia. There was a decades-long conflict, and this was trying to end that. Once this agreement was reached, then they sent it out for a national referendum. And then referendum narrowly failed, but what was especially interesting to political scientists in this vote data is the high degree of heterogeneity across different regions of Colombia. And that's kind of what this map is showing here. You can see I haven't put numbers on this heat map scale, but across the different regions, the support ranged from under 20% to 96%. So there's a huge range in values here. And you can see that there were many regions that were highly in favor and others that were very opposed. So this is very interesting to political scientists to understand, why do people feel so differently about this deal across Colombia? Two of the big hypotheses that have been put forward, one has to do with exposure to violence, the idea that certain regions experience the conflict very differently than others. Those regions tended to support the peace deal, where regions that were untouched didn't feel strongly that it needed to be ended or that the peace deal needed to happen in this way. Another very different hypothesis is that the vote isn't really commenting on the conflict or the peace deal itself on its substance, but on the president of Colombia, who was the one who negotiated this peace deal and who made it a big part of his electoral platform. And so the thought is that people who liked the president in 2014, when he was first elected, still like him in 2016. And if they don't like him, they're voting against his peace deal. So what I'm going to try and do is test both of these theories kind of empirically using data. And to do that, I'm going to reframe both of these stories about why people voted the way they did as stories about causal effects. So basically what I'm imagining here is a counterfactual version of this sort of 2016 Colombian vote, where we imagine that fewer or different regions had been impacted by violence, or fewer or different regions had supported the president. So it's the presidential support one is a little weird to think of as an intervention, but you can imagine maybe in 2014, when the president ran his campaign, he sort of made different electoral promises or focused his campaign activities in different places, and maybe that would have changed how people felt about him back then. So for each of these different treatments, I'm going to think about them in a binary way, right? Either there was violence in this region during the 5 years prior to the referendum, or there was not. and either this region supported the president with more than 50% of the vote share in 2014 or not. And I'm going to code things in this binary way. And then I'm going to kind of ask you to imagine this sort of hypothetical experiment where, as researchers, we were able to go in and assign these variables, perhaps by fair coin flips or something like that, to each individual region in Colombia. So the reason this is even useful to think about is that if we could have done this, right, then if we collect all the regions with a z equals 1 value and the regions with z equals 0 value, they should basically be comparable in every way, except on average, except for the thing that we've introduced, right? These fair coin flips aren't going to sort poorer or more populous regions into one of the two groups. Of course, in real life, it's not a randomized trial, right? The regions that were exposed to violence look very different from those that weren't, and same thing for presidential support. But if we just kind of follow this thread for a second and think about measuring the impact of these treatments Z, we can do that kind of mathematically using potential outcomes, right? I'm going to let yi of 1 represent the counterfactual vote share that would have been observed for region I in the case that it was treated, whether that's exposure to violence or presidential support, and yi0 will represent the other possibility under control. And using these quantities, we can define something we might be interested in measuring, right? Which is the average treatment effect, in this case, across the treated. So for exposure to violence, say, this is telling us what's the impact of violence on the vote share among the type of regions that tended to experience violence. Again, if we had our sort of hypothetical randomized trial, this would be quite easy to estimate. We would just have to take an average of the regions getting treatment, the vote share in those regions, and subtract the average vote share in the regions not getting treatment, and this would be a good estimate. But in observational studies, this doesn't work, right? Because these regions getting treatment, they tend to have different baseline factors, right? Maybe they're poorer regions, maybe they're higher in elevation, which is an important dimension of variation in Colombia than these regions. And so based on those differences, we'd already expect the vote shares to be different. And so this is going to give us a mix of that bias and the effect we care about. So one way we can attempt to fix this problem is by using a weighted estimator. So this is exactly the same formula as the one in the middle of the slide here, except that we have these wi hats, which are now present in the control mean, right? And every summation, we're going to put in this wi hat. So what does this mean? Where does it come from? This is basically just a function of the pre-treatment covariates. So I mentioned we see these baseline differences to begin with. They're quantities we measure about all the regions of Colombia. We can see differences. We're going to construct these wi hats as a function of those x variables. And intuitively, what we're doing is we want to take control in regions that don't look at all like the treated regions and give them very small weights. And we want to take the regions that do look a lot like the treated regions and give them large weights. And so that's all the weights are doing at a high level. One really common way to specify these weights is by fitting a propensity score, right? You fit a model to predict exposure in terms of the variables. And then you basically use a particular transformation of that as your weight. And that will, in large samples, tend to drive this kind of balancing condition. So just a small note on kind of a notation here. The wi hats are what we're actually going to use in practice in this estimator, right? We have to estimate this propensity score. But in a lot of the talk, I'll be focusing on the population version of this, which just kind of assumes that we know the true propensity score. So just keeping track of what W and W hat mean. Okay, so an important question is, does this weighted estimator actually work? Is it, we can try this, but will it actually measure the thing we want? The answer is yes, under certain potentially very strong assumptions. And I'm not going to go through all of the assumptions even today. There's several more that I don't have time to talk about. But the one I want to talk about is what I think is the most important one and the one that's probably most suspect in practice, which is the conditional ignorability assumption. And this basically says that we've measured all of the important confounders, right? That everything that explains covariation in the potential outcomes and the treatment is measured and is going into our weights. So if this is true, and these other assumptions that I'm not mentioning today hold, then this weighted estimator is going to be consistent for the effect we care about. But if we miss anything, if there's any pretreatment covariate that we did not measure, that is unobserved, and that remains left out of our weights, basically our weighted estimator will be wrong. It's not going to converge to the right effect. So this is a big problem just in practice, right? Because almost always, somebody in your seminar can think of a variable that you didn't measure that is going to be contributing a little more bias, right? And so it's really important not to just expect people to believe this, but to be able to say something about robustness to this assumption. And so,
I'm just gonna, sorry, somebody asked in the chat, is this like IPW?
yes, yeah. So I think more generally, you can think of other kinds of weighting methods as well for what I'm going to talk about. If you're familiar with balancing weights methods or entropy balancing or things like that, the ideas in this talk should apply to those methods as well. But I'm focusing on the case of IPW, and that is probably the most dominant way to do this. Yeah, great question. Okay, so this gets us to sensitivity analysis. In sensitivity analysis, what we're trying to do is demonstrate robustness of our effect to small violations of this assumption. Okay, so let me give sort of a mathematical description of how sensitivity analysis works for weighted estimators. We're going to say that conditional ignorability may actually be violated. So our weights, these weights W that we can compute or estimate from the observed data are going to be wrong. Actually, the weights we want are these different weights, W star. But we're going to say the W star weights, the true ones, are not that different from the Ws. They're close in some sense. There's some error metric. We have to kind of pause it here. And we're going to say that on this error metric, the Ws and the W stars are close. Obviously, the bigger we make this gamma parameter, the more unobserved confounding we're allowing for. So this is flexible in terms of thinking about how much confounding you're worried about. For any given value of gamma here, what you want to do at this point is figure out for this kind of family of possible W stars, the true weights that you didn't get, what's the range of possible point estimates, right? And if you can figure out this range, that intuitively tells you how much bias you may have in your estimate. And it will allow you to say, basically, you're hoping this range is very small, right? And then essentially your effect is going to be robust. In practice, right, these depend on population quantities, so we're going to wrap a confidence interval around it. In practice, also, we may not just sort of pick some arbitrary value of gamma and run it for that, but we may run this analysis for larger and larger values of gamma and see how big a value of gamma it takes before this interval crosses 0. Okay, so that's the high-level story. Right now, this description of sensitivity analysis is still pretty abstract, though. I've told you this is some error metric. I've told you this is some parameter. In practice, there are many different ways to choose this error metric and this parameter to give you a particular sensitivity analysis that you can actually compute. And so I'm going to focus on one of those for the purposes of the talk today. At the end, if I have time, I may talk about another one. But what I'm going to be focusing on is what's called the variance-based sensitivity model. This is actually recent work by my co-author, Melody Huang. And it's a really nice way, I think, to think about just to parameterize the difference between the weights you got and the weights you might have wanted. Essentially, what we're saying here is that the W stars, the true weights that we didn't get, a certain amount of their variation has to be explained by the Ws, right? And we're going to restrict how much extra variance or variation there is in the W stars that's not already explained by W using this R² parameter. So when R² is close to 1, this is saying that almost all of the variation in W star is unexplained by W. That's allowing for a lot of unobserved confounding. When we make the R² close to 0, then that's saying almost all the variation W star is already predicted by W. So the unobserved confounding is going to be small. One thing that's nice about this method, I guess I'll say one thing that's important to note about it is it's kind of an average case notion of unobserved confounding. So this doesn't rule out the possibility that there's a couple of regions where our weights are really, really far off. It's saying on average across the kinds of regions that we'd like to see, then in general, that's kind of the way it's thinking about measuring unobserved confounding. Another thing that's nice about this is that you can get closed form bounds for the partially identified region. So you don't have to sort of rely on a numeric solver. There are formulas that you can just plug in your R² and your weights, and you can figure out how wide those that interval is going to be. There's also a way to do more computation and get slightly sharper bounds, but in practice, these aren't that different. So I'm going to focus on the closed form bounds for the purpose of the talk. Okay, so the upshot of all this is that in a study, we can do something like this. And this is actually the variance-based sensitivity analysis run for our presidential support treatment. Here's our point estimate where we assume there's no unobserved confounding. And you can see that as we dial up our R² parameter and allow for more and more unobserved confounding, then the bounds on our partially identified region grow, right? And that's kind of what's driving the fact that these intervals get wider. Eventually, they're going to cross 0. And so this is probably what you'd report in your paper, right? You'd report this estimate, and then you'd say, this effect is robust to unobserved confounders up to R² equals 0.25.
So R squared, is that something that you would like elicit from somebody, perhaps like a practitioner?
Yeah, that's a great question. You could, right? Yeah, so that would be a slightly different kind of workflow than what I'm describing here. Here, I would say, yeah, you just do them all until you find the point at which it crosses, and then you present that as something for practitioners to think about. If you had a really specific idea about what kind of unobserved confounding you were interested in, you could instead elicit that R squared, and you could just do the interval for that R squared, right? So that would be a different way to use this tool. Great. So far, this has mostly just been review, right? These are ideas that are out there in the literature at all. Personally, I think this is a great way to think about unobserved confounding, and that's something, maybe it's not totally satisfying, but at least it's quantitative, and it's something you can put out there that's making a clear claim about unobserved confounding. One of the big drawbacks of this approach, though, is that it's typically done all completely post hoc, right? So you're going to work really hard and think very carefully about how to generate this estimate. And then all of this stuff is just kind of slapped on at the end. So one thing that can happen that's a real, a real shame is if you work so hard on this and then you do your sensitivity analysis and right away for very small values of R squared, these intervals explode and show that your design is very susceptible to unobserved confounding. That essentially undermines your whole story, right? If you have an effect that seems significant, but then it's susceptible to very minor amounts of unobserved confounding, no one's going to believe this is a real causal effect. And it's sort of too late at this point to go back and change this initial analysis now that you've looked at the outcomes, at least kind of from the design-based perspective. So what I think would be useful is some kind of tool that lets you, before you look at the outcomes, at the time you're setting up your weighted estimator, anticipate what that sensitivity analysis is going to look like, and potentially to optimize your design, to think about different design choices you could make that is going to make it more robust. And so that's kind of what I'm really here to tell you about today is this design tool called design sensitivity, newly developed for weighted estimators, which it's sort of like a power analysis for the sensitivity part of your workflow, and will let you sort of anticipate how sensitive your estimates are going to be and potentially change your design to make it more robust. So kind of the roadmap from here, I want to talk about the idea of design sensitivity, what it is. It is indeed closely related to power, so that's kind of where I'll start. And by the way, this idea, although it's new in the context of weighting estimators, it actually goes back to much older work on matched design. So we're very, very much indebted to and building on. So once I've kind of given you the tool, I'm going to circle back to the Colombia example, and we're going to talk about how design sensitivity helps us make concrete choices about our weighting estimator that actually improve its robustness in this particular study. And if there's time at the end, I may comment briefly on a different sensitivity model. So applying all these ideas to a model that indexes unobserved confounding quite differently. Okay, so let me start by talking about design sensitivity. And yeah, here we're going to start with kind of a quick review of statistical power. So if you have a hypothesis test with that you can invert and turn into a confidence interval, you can describe the power as the probability that the confidence interval excludes zero under what I'm going to call a favorable situation. Right? So typically in power analysis, this involves assuming that there is a treatment effect, and typically you decide how big that treatment effect is. You just posit some treatment effect of interest. And then you also usually have to make some kind of assumptions about the distribution of your outcome. Sometimes this is just an effect variance. Sometimes you maybe need a few more assumptions. These two things together, they sort of let you write out exactly what the alternative distribution is going to look like. And then you just compare it to the null distribution, which is more often known. And you get this you can compute the power as the probability under the alternative that the alternative lies above the critical value, right? Okay, I'm now going to take this idea of power and generalize it slightly to the power of a sensitivity analysis. And the big idea here is, just going back to this picture for a second, power is basically the probability that this interval is going to exclude zero. All I'm saying with power of sensitivity analysis, I'm thinking about one of these intervals instead. Right, I'm allowing for, that we don't actually know right where the point estimate should be. There's going to be a partially identified region. We need a wider interval, but I'm still interested in the probability that this interval excludes zero. So that's, obviously it's going to be a bit lower than power if we assume that there's no unobserved confounding. And kind of why that happens, right, is we sort of have to, our null distribution is going to move a bit to the right, right? We don't know where this null distribution should be centered because now we have this partially identified region, so we have to kind of shift the null over to the worst case setting and work with that, and that's going to make our power lower. But very much the same kind of idea. One other sort of kind of technical point here is that the favorable situation now, it includes both that there's a true treatment effect, some distributional assumptions about the outcome, we're also going to assume that unbeknownst to us, in reality, there is no unobserved bias. And this may seem a little weird, right? Because the whole purpose of sensitivity analysis is to let us deal with unobserved bias. But, I guess the big idea is that in real life, if you have an observational study, you're always going to have to do that sensitivity analysis because you don't know that it's absent in terms of understanding like what the best case would be to measure your treatment effect. It's still reasonable to think about comparing what you know, which is you're starting with this null distribution and you're allowing for unobserved confounding, to the truth, which is that there is an effect and there's no unobserved confounding. This is very much kind of the weirdness of power analysis, right? Where you're assuming two kinds of things at once. So hopefully this sits okay with people. Okay, so assuming that we're okay with this idea of power of a sensitivity analysis, that this is something interesting we might want to calculate, and we can think about how to do that, let's think about some of its operating characteristics. What is going to make the power of a sensitivity analysis bigger or smaller? One thing that's going to matter is the variance of our outcome or of our estimator. And this is kind of how sample size tends to influence things, right? If we make these distributions really concentrated, they'll overlap less, we'll have higher power. Another thing that matters is effect size, right? If you take your alternative and you shift it, then you're going to have higher power, at least if you shift it in that direction, right? A final thing that matters, and this is actually specific to power of a sensitivity analysis rather than power more generally, is the sensitivity parameter, right? If we make our sensitivity parameter bigger, if we allow for more unobserved confounding, this partially identified region is going to get wider, the null distribution is going to shift over here, and we're going to have less power. So here is a formula that basically tells you what I just said in math in perhaps a less clear way. But I think this formula is still interesting for reasons I'll get to in a second. And by the way, this formula also kind of was originally derived by Rosenbaum. We kind of re-derived it for our case. So there's a lot going on, a lot of different subscripts and Greek letters here. Let me just walk through a few of the key pieces. So in this power formula, one term just depends on alpha. That's not very interesting because we don't really change alpha. Another term, these sigmas, are going to, this is basically where the information about the outcome variance comes in, right? And so if you have a highly concentrated outcome or distribution, then these will be small and that will tend to make power higher. But the most interesting term going on here is this difference between two quantities over here. So the tau here is our true effect under the alternative. In the picture, that's the center of the blue distribution here, this gray dotted line. The other term, this xi, is going to be, if I got that Greek letter right, I was getting mixed up. That one is the top of the partially identified region, right? And so the key, a key quantity in this power formula is the gap between these two numbers. What's especially interesting about the role of this gap, if you look at this formula, is that there's this root n kind of multiplier on this difference. So that means a couple of things. One thing it means is that as n gets large, the importance of this term relative to these others is going to be huge. And basically, these things are going to vanish. And this is going to be the only part of the power formula that matters. The other thing, which is a little more subtle, is that as n gets large enough, the magnitude of this difference actually isn't going to matter either. And what's really going to matter is the sign. So if we, for any given value of this difference, if we make n sufficiently large, then power is going to be high as long as the partially identified region doesn't exceed the center of this distribution. But then as soon as it crosses, power is going to collapse. So we can see this playing out in these power calculation plot. So what's going on here is I'm plotting power on the y-axis. I have a sensitivity parameter, gamma, on the x-axis. So unsurprisingly, and each of the lines is a different sample size. Okay, so for any given sample size, kind of makes sense. As you increase this parameter, power is going to go down. Another way to look at this plot is to take a vertical slice and look at, for a given value of gamma, what happens as we take n to infinity, right? So over here, right, where gamma is near 0, then you can see as n goes to infinity, power goes to 1, which is basically what we usually expect to happen with power. But if you go to a different part of the plot, if you go up here and you cross this sort of key boundary, then all of a sudden it doesn't matter how much data you have. Even if you have infinite data, you're still not going to be able to detect the effect. And that's because you've now allowed for so much unobserved confounding that the data is basically saying, look, I can't tell if this is an effect or unobserved confounding. So and so this is kind of related to that behavior with the phase transition, right? Essentially, there's this wall we hit. There's a very particular value of gamma, which is in fact the value of gamma that makes these two numbers equal. Below that, if you have enough data, you're going to be able to detect the effect. Eventually, data can help you overcome the problem of unobserved confounding, as long as unobserved confounding is only up to this level. But when there's more unobserved confounding present, then it doesn't matter how much data you have, you're kind of sunk. You can't estimate the treatment effect. Okay, so I think this is super interesting mathematically, but let's also think about what it means practically. If you're designing a study and you want to make sure your study is as robust as possible to unobserved confounding, and let's say you have a decent sample size, so you're not dealing with really tiny samples, you have a pretty large N, then essentially the thing you should be most worried about is this number, this design sensitivity, right? If you can make this number, if you can do something in your design to make this number large, that will give you, that will mean that up to that level, higher level of unobserved confounding, you have confidence that you'll be able to detect an effect. Whereas if it's small, then having all that data isn't actually going to help you. And so, where I'm going from here is I'm going to try and compute this number for different designs, and I'm going to try and think about how to make it as large as possible to guarantee that we have high power in our sensitivity analysis, even for large values of gamma. Okay, maybe I'll pause here just for a second. This might be a good time for a clarifying question, if anyone has one. Okay, I hope that means I haven't just totally lost people. So, okay, so at a high level, I think hopefully people are on board with this idea of design sensitivity. Yeah, let's calculate this. Let's use it. I haven't really told you actually how to calculate it, though, right? This is some kind of abstract solution to an estimating equation. It turns out for the variance-based model, we can actually get a nice closed form expression for this, which comes again from the closed form bounds that we started with. And here's what design sensitivity looks like. I'm going to indicate design sensitivity with this little tilde thing on top of the R squared. Right. So basically, design sensitivity is it depends on three quantities, all of which are observable to us. One is the correlation between the weights we can estimate, the W's, and our outcomes under control. One is the variance of those weights, and one is the variance of the outcomes. Right. So big picture, having this correlation between W and Y be large, that's going to be a good thing for design sensitivity. Right. If W and Y are already highly correlated, there's not much extra variation in Y left over to be sort of adversarially explained by some confounder that's going to break things for us. On the other hand, if these variances are big, then that means there's more heterogeneity in our study, and there's more opportunity for that sort of adversarial confounder to be correlated with that heterogeneity and kind of mess up our lives a little bit.
Quick clarifying question.
Yeah.
What's TW?
Tau W is the effect size. Yeah, this is the, going back to the picture, it's the center of that blue distribution, right? So yeah, so yeah, that's a really good point. I haven't called that out specifically because we can't actually see this, but clearly if you have a much bigger effect size, you are going to have a much bigger design sensitivity as well. So that also matters a ton in this. Okay, so using this formula, we calculated design sensitivity for our two treatments in the Columbia study. Just a side note here, in order to calculate this, you actually need to know some things about the outcomes. And sort of the whole point of this is that we're doing it before we look at the outcomes. So to make these pictures, I actually cheated a little bit and used the observed outcome distributions. But just in practice, what you might want to do instead is take a small pilot sample of your data. And if you do that, we actually tried that in our data and we got pictures that looked very similar. So that's something you can do in practice to essentially calibrate the parts of this formula depending on why. Okay, so going back to these pictures, this is really interesting. It's telling us something is very different between our two studies, the one with exposure to violence and presidential support. For presidential support, what we're seeing is if in real life there's going to be a large effect size for presidential support, then we also expect to be able to detect that effect size and that it should be fairly robust to unobserved confounding, right? If the effect size is 20 points, then that corresponds to a design sensitivity here of around 0.55 or 0.6, something like that. That means that if the true effect is indeed 20, we expect to be able to identify that effect in large samples, even allowing for over half of the variation in W star to be unexplained by W. So that should give us, that's comforting, right? That's a sign that maybe we can go ahead and run the study and those intervals won't explode too quickly. On the other hand, we have kind of the opposite story for exposure to violence. This is saying that even if we have a truly massive effect size for exposure to violence, then that's likely to be very sensitive to unmeasured confounding. And we're likely to be unable to rule out the possibility that a mild confounder could explain even this very large effect. So this is pretty disappointing news, right? This basically tells us that this is exactly the kind of behavior we were worried about when we set out on this course to calculate design sensitivity, and that maybe there's something wrong with the study, something that we should change about it before we go ahead and do all the work to run it and find out that our results are sensitive. Okay, so that's the next piece of the talk is what do we do with this study? How do we think about improving it, so that it's more robust and measured confounding?
Just to make sure I'm following. So
yeah,
is the idea that you can trace the the sort of fact that for large effect sizes there's low design sensitivity in the left study to one of those three terms in the previous theorem, like the covariance or the two variances, like something is larger than it should be or smaller than it should be.
Yeah, that's great intuition, and it'll come up later, but essentially one of the reasons we end up having low design sensitivity here is that there are some extreme weights in this study. And so if you think about these terms, I think the culprit is probably the variance of the weights, and that's what's driving this. Sorry.
Can I ask a quick clarifying question too?
Yes.
When you say effect size here, you don't mean effect size in the psychology version of it in standard deviation terms, right? You're saying effect size on the scale of the outcome variable for your study?
Correct. Yeah, I'm talking about the number, the shift in the percentage points of vote share. Yeah. So an effect size of 30 would mean that if your region is exposed to violence, then in the 2016 national referendum, you're voting for that at 70% instead of 40%. So these are pretty huge effect sizes that we're talking about here.
Yeah, but less huge than it would be in that.
Yeah, good point. Yeah, not really that huge. Yeah.
Okay, thanks.
Yeah, great question. Thanks. Okay, so let's see what we can do now to try and fix this exposure to violence study. And again, design sensitivity is going to be super useful to us here. But before we can see how design sensitivity can help us, the first thing we have to think about is, okay, we had in mind to do this weighted study. What could we be doing instead? How could we be changing up our design strategy a little bit? So one thing that is commonly done in weighting studies is to bring in an outcome model, right? And this is known sometimes as augmentation or augmented estimators. It's also known as doubly robust estimation. Briefly, the idea is you fit a model for this, in our case, 2016 vote share in terms of the x's, right? And you get these fitted values, g hat. And then instead of just taking a simple weighted average of the yi's, you now have an average of the g hats, and then you have a weighted average of the residuals of the yi's. This estimator is described in a lot more detail other places. I'm just kind of, presenting it here. I mentioned that this is called doubly robust sometimes, and one of the main statistical kind of theoretical arguments for using this estimator is that it turns out that if either your propensity score model in which the weights are based is right, or your outcome model is correctly specified, either one, not necessarily both, you still get consistency. And so this is seen as a big advantage that you don't have to rely on any one model to be correct. So personally, I find this a little unsatisfying in a world where we believe unobserved confounding is present, because if unobserved confounding is present, we know that both of the models will be wrong. Kind of the definition of an unobserved confounder means that it shows that if it's a confounder, it has to show up in both of these models. If it's unobserved, both of those models are going to be wrong. So I've always found that a little disappointing. And there's also been some work, although there's been a lot of kind of back and forth about this paper and how and exactly what its implications are. But there is some evidence, at least, that when you use a doubly robust estimator and both models are wrong, that it can be worse than using one of the simpler weighted or regression estimators. So I would say that right now, the literature is not super clear about whether it's a good idea to use this in a setting where you think unobserved confounding is present. But this is a great thing for design sensitivity to look at, right? Because design sensitivity is really designed to help us think about the operating characteristics of methods when we're in a world with unobserved confounding and when we're trying to account for that. So we went ahead and calculated the design sensitivity for an augmented estimator. And it's actually pretty easy to do based on our earlier calculations. Basically, as long as you're assuming the outcome model is fit out of sample, which we assumed, then all you're doing is basically replacing y's everywhere in these formulas with these residuals, right? And based on that, we came up with this formula for when an augmented estimator should have a better design sensitivity than the regular weighted estimator. And the big story in this inequality is that the variance of the residuals after augmentation has to be less than the variance of the original outcomes after multiplication by the scaling term. So first of all, let me point out that if you have any halfway decent regression method, it should reduce the variance of the residuals. This variance should be smaller than y. That's kind of the whole point of regression. So basically, as long as nothing too crazy is going on with the correlation structure between the weights and the residuals, and as long as the residualization isn't changing this correlation structure in some kind of pathological way, we should almost always expect this condition to hold. We should almost always expect this thing to be less than this thing on the right. So this basically tells us that almost any time we're fitting an augmented estimator, we should expect it to help us with design sensitivity. And this is actually true whether or not the model is correctly specified. We make no assumptions here about the model being right. Basically, all it has to do is do a good job of reducing variance in our outcomes. So I think this is pretty interesting from sort of a, from a perspective of making a case for the doubly robust estimator, right? Most of the cases I've heard involve assuming ignorability and making this argument based on consistency to things. This is a very different kind of argument that doesn't actually rely on correct specification at all. But I find this one maybe a lot more convincing in the kinds of problems that I work on. And in fact, we can see this play out in our two treatments, right? For both presidential support and exposure to violence, augmenting helps us. We're looking at several different hypothetical models that explain different amounts of variance. And you can see that the better the model is, the more it's going to boost our design sensitivity. So that's great news. The bad news is that this is better, but it's still not good, right? Even this high line, if we could explain 50% of the variance with our regression model, it's still not a great design sensitivity. We really want this number to be much higher before we feel good about running our study. So what's something else we can do here? A different way we can change up our estimation. Another thing we can do is trimming. Okay, and trimming basically just means finding observations in our data that have very large weights and getting rid of them from our study. So this is discussed in a few different ways in the literature. The most kind of formal characterization that I am aware of is in this paper by Crump and co-authors, where they basically said, okay, what we're doing here, if we follow this practice, is we're redefining our estimate. We're saying instead of estimating the ATT overall for everybody in the study, we're going to estimate it for a subset of people who don't have crazy huge propensity scores or crazy huge weights. Okay, so from a policy perspective, this is kind of a weird thing to do. Probably, there's nothing from a concrete perspective that's fundamentally different about these people that you wouldn't want to include them in your analysis. This is more of a story about a bias variance trade-off, right? If you have huge weights in your study, that's going to make your weighted estimator have massive variance. It's going to be really hard to find significance because your confidence intervals are going to be huge. Maybe it's worth it to estimate the wrong estimand, something that's maybe slightly off from what you really care about if it makes your variance small. So that's kind of the discussion around this trimming approach in the literature. And again, all of this assumes that there's no unobserved confounding. So how does this story change? What are the implications for trimming in a world where we are going to do sensitivity analysis? We worry about unobserved confounding. Again, design sensitivity is a tool that lets us think about this.
That's good. Maybe a super naive question. So I don't know anything about trimming, but I'm wondering whether you could make the idea of trimming sound more sensible by searching over subgroups to find subgroups where the weights are not
yes
aren't close to 0. Or you could be like, oh well, that's at least a reasonably defined group, but now I'm just talking about.
Yeah, that's a great question. There's actually an excellent paper by Dylan Small and Mikhail Traskin where they basically do that. They sort of start with kind of a propensity score threshold like this and then say, okay, let's try and understand what we're really doing here. And they try and come up with an approximation to this population that's actually based on box constraints on actual variables. So I think if that's what you wanted to do, there is kind of a recipe for how to do that. And that would, I think you're right, that would be a good, if you were worried about this bias, that would be a way to sort of really be upfront about what you're doing. Okay, so we're now going to do the same analysis we did before for augmentation with trimming, where I'm going to we calculate the design sensitivity for the trimmed estimator, and we're going to come up with a condition under which that design sensitivity is going to be better than what we got for the regular estimator. So basically, this formula is a little more complicated and it's much less obvious, in general, what we'd expect here. The big story, right, is that trimming is going to reduce the variance in our weights, right? And that's a good thing, right? Having highly variable weights is bad for design sensitivity. But this variance may be offset by other kinds of things that trimming could do. Trimming might actually, it might change the relationship between W and Y. It's a little unclear what its impact will be on the variance in the Ys. So, we spend a lot of time looking at this formula, and it's hard to kind of abstract a general rule that, yeah, in general, trimming's good, in general, trimming's bad. But the good news is, because of the way design sensitivity works, you don't have to rely on a general rule like this to decide about trimming. You can actually calculate design sensitivity for your study using your own weights and your sort of best guess for your outcome distribution. And you can decide in any particular study, does trimming actually make sense? And so we did that for our two treatments. And what we found is that trimming has a massively beneficial effect, especially for this exposure to violence treatment, right? All of a sudden, when we trim just a fairly, 10% of our observations, then we're going to shoot all the way up here to having a very high design sensitivity for a large effect size. So Ravi's question earlier kind of hit at like why this is happening. Basically, it turns out there's one region in our exposure to violence weighting estimator that has a really, really massive weight. It turns out one of the covariates that we're using in our exposure to violence treatment is, the exposure is defined by violence in the 5 years just prior to the election, but we also have data about violence prior to that. And unsurprisingly, most of the treated units have violence in the 10 years prior to the exposure period, and most of the control regions don't. There's one very weird control region which has a lot of violence in that 10-year period and then none in the 5-year period, and that is getting tons and tons of weight in the analysis. So, I don't know enough about Colombia to understand like the implications of excluding that one particular region, but it does seem like from a statistical perspective that region is causing problems for us. And when we kick it out, then everything suddenly becomes more robust and more stable. Again, we probably could have guessed that it might be a good idea to exclude this region just based on understanding of variance and bias variance trade-off. But what design sensitivity is telling us is this is also going to be really beneficial for our sensitivity analysis, which I don't think is something that would have been easily understood without these tools that we've got. Okay, so in a lot of ways, this is kind of the end of the story. This is kind of the pitch for design sensitivity. It's something that we can look at in advance before we dive in and do this terrible study, and hopefully it helps us find a way to do this study instead, right? Maybe because I've got a few minutes, I'll very briefly talk about a different sensitivity model, right? Everything we've done so far has been working with these R-squareds, this way of thinking about unobserved confounding. That's actually not the most common way to do sensitivity analysis for weighting. The leading method is instead this thing called the marginal sensitivity model. And this is, so again, we're starting with this idea of some error metric and some bound, but now the error metric is just going to be the ratio between any individual W star and W value. And this is not an expectation or an average anyway. This is saying of all of the possible different values of W star and W, we're taking the absolute max and the absolute min, and we're capping how big that can be. This is basically an L infinity norm instead. So it's a very different way of thinking about unobserved confounding. It's a very worst case sort of thing. Even if there's only one weight in your entire study that where you have a difference this big, then that's the number we're going to use. But it also provides really powerful control, right? Because you're ruling out the possibility there's any really massive confounder. So I think the question of whether it makes more sense to use the marginal sensitivity model or the variance-based model is a really interesting and complex question that I don't have time to talk about in the talk today. And honestly, it's a big focus of my future research, is trying to figure out, among all these metrics, how do you think about, especially as a practitioner, choosing among them? So the earlier paper that I wrote with Melody about variance-based sensitivity analysis digs more into these questions. Just a few kind of key points. Marginal sensitivity analysis is a bit more like matching-based approaches of sensitivity analysis. If you're a matching person, maybe this feels like a better way to do it. The variance-based model is closer to things like the Sinelli-Hazlitt approach to sensitivity analysis for regression. So if you're using the SenseMacher package, doing those kinds of sensitivity analyses, this is probably a better variance-based modeling is more kind of spiritually akin to that. Also, if you're worried about the possibility that certain weights are just very, very different, there are maybe rare cases of very extreme unobserved confounding, the variance-based model gives you a way to think about that the marginal sensitivity model does not. And that's one of the big themes we try and bring out in this earlier paper. But in our design sensitivity discussion, it turns out you can come up with design sensitivity for both of these models. I presented the variance-based version because the formulas are a little nicer, but everything works fine for for the marginal model as well. So here, for example, is our construction of design sensitivity for the marginal model. Again, the formula is a bit ugly. It's not a closed form. This is an estimating equation you have to solve, but you can solve it numerically. As long as, again, you have to make some assumptions about the outcome distribution. But once you do that, and if you have a planning sample, it's not hard to calibrate that. You can get these numbers. So the final thing I want to show you from this marginal model is I'm going to show you the counterpart plots for looking at augmentation and trimming across our two treatments for the marginal sensitivity model on the right, compared to the ones we got for the variance-based model on the left. So you can see here that the augmentation is very beneficial for the marginal sensitivity model, maybe even a little more so than the variance-based model. As we fit better and better outcome models, then our design sensitivity is going up. What's sort of weird is that trimming is actually not helpful for the marginal sensitivity model. The lines are going slightly down when we trim a little bit. So in purely abstract mathematical terms, this isn't a total surprise, right? We're parameterizing unobserved confounding in very different ways. It sort of makes sense that different things might drive the performance of design sensitivity, which are now two very different kind of measures. From a practical perspective, though, this is kind of weird and unsettling to me. I think my best takeaway from it at this point is that it's really important, if you're gonna approach your design this way, to pick in advance which sensitivity model you want to use, and to sort of decide as your first decision, this is how I'm going to do sensitivity analysis. And then once you've settled on whether you're kind of on the right here or on the left, then you can calculate the appropriate design sensitivity and make the right call. But the right decisions to make about your design are actually the context of how you're going to think about sensitivity analysis actually matters a lot for what's going to make your design most robust. Okay, let me just wrap up here. Again, the big picture here is that you may want to know before you run your weighted study what that sensitivity analysis is going to look like. Design sensitivity gives you something you can compute that will give you a sense for that. Design sensitivity exists actually much more generally than just these two models I've showed, right? Our main result says for any time we have a metric and a bound, we can kind of, the design sensitivity should exist. It should be there. For these two particular models, we can actually calculate it without, needing infinite computation time. And so that's something you can actually do in practice. And then once you are starting to compute these design sensitivity numbers, you can then use this to sort out different choices about your weighted estimator and kind of optimize that for robustness to unmeasured bias. So there's tons and tons of future follow-up opportunities here. One thing we could do, right, is we could start thinking about more kinds of sensitivity analysis. I've basically showed you an L2 type sensitivity analysis, which is the variance-based model, and an L infinity type. In the literature, people have been talking recently about L1 sensitivity analysis. I still don't have a really clear idea in my mind of why exactly practitioners would care about that. But if you did, then the design sensitivity would be important, and that would be a whole other, project to do, is figure out how these formulas for that method. Another really important question is what other design choices could influence design sensitivity, right? We've only talked about augmentation and trimming today. Trimming is maybe a special case of something we could do more generally with weighted estimators, which is change up our estimate, right? And I'm very interested in things like, we focused on ATT today. What if we did ATE instead? Would that have implications for design sensitivity? Or what about quantile effects? I think, with pure conjecture, is that I think quantile effects may be more robust to unmeasured bias than average effects. I don't really have a lot to back that up yet, but I'm very interested to get into that and find out if it's true. And a final thing, right, is we've talked about weighting today, but regression can be represented as a weighting problem. So I'm also really interested in thinking about how to take all these ideas and apply them to regression, right? I think my guess is that showing that design sensitivity exists for regression in whatever sensitivity analysis framework you're going to set up there is going to be possible. And I think the real work there is figuring out, okay, what are the design decisions we're making in regression? Like, and how are those things going to move the design sensitivity around? How should this change the way we think about specifying a regression model? But that's all I've got for today. Thanks very much for your attention. And here's the link to our if you're interested. Thanks.
Thank you. Let's open it up for questions.
People are usually, I don't know, sometimes it helps to get the ball rolling. So I'll throw out a, which is, you can either think of it as a softball or an impossible question.
Okay.
So first of all, this is amazing. This is lovely work, and really, like, getting people to be more thoughtful about the design part is fantastic. So thank you for this. One thing I particularly like about it is that, as opposed to some of the more traditional sensitivity analysis frameworks, you're bringing in the outcome, right? Which when that gets ignored, it seems to be extremely problematic to me. So that's fabulous. But then it does leave you in this position of like, you're a little hand wavy about like, oh, well, just if you have pilot data, great, move on. But like, what if you don't? And this happens in power analysis too. Like if you've never done it before, you're always like making up numbers. So maybe that's just what you do, but any guidance about that?
Yeah, that's a great question. And yeah, this is definitely something I struggle with in my applied work too, right? Where you have like not that much data and you're like, oh, I don't really want to like sacrifice any of this. Yeah, I mean, I think you're totally right that the right way to think about this is from the perspective of power analysis, and that whatever choices you'd make for power analysis, you can make here too. I mean, the nice thing about design sensitivity computations is they're kind of free in the sense that you can, you could make some outcome assumptions, you could run this whole analysis, and then you could make very different outcome assumptions and you could run it again. I mean, that's actually, maybe that makes the decision process harder, right? And maybe it's hard to organize all of the different outcome models you want to think about. Maybe that makes for a very messy early stage kind of what the design stage actually looks like, because you have to go through many different hypothetical outcome models. But in principle, you can do that, right? I will say, though, I think anytime you can have a pilot sample, even if it hurts a little bit to create that pilot sample, I think there are huge benefits to doing that. I mean, I guess part of this is motivated from coming from the matching world, where I think that's a very extreme version of the treatment-only approach, where basically people don't touch outcomes at all until the very final step when they do the analysis. And the more I've been exploring these ideas, the more I'm realizing, like you said, how important it is to bring in the outcome model. And so I think even if you're a very design-based person, you like to think about doing everything in terms of the treatment model, and you don't have a huge sample size, if you can sort of spend a few of your control observations to take this pilot sample, I think the information that gives you about the outcome analysis is useful not only for design sensitivity, but all kinds of other things that will, improve the quality of your estimation and help you choose the right variables to weight heavily in your kind of in your weighting approach. So I'm a big advocate for taking pilot samples wherever we can.
I have a very naive question. So I understand I clearly understand the process of what trimming looks like the implementation that's very straightforward. Could you talk more about the implementation of the augmented method?
Yeah, that's a really good question. So I think the ideal version that I've presented here, and this again connects this idea of pilot samples, right, is that you have your data, right, in which you're fitting your weights. And then you have this outcome model that's coming in from somewhere else, right? And that you can, so maybe if you have a large pilot sample, you fit the outcome model there, right? And now you're bringing it in. And so basically what you have is a set of coefficients, and then you're computing the fitted values on the data in there. I do think that a lot of accounts of the doubly robust estimator in the literature think about using some aspects of the same sample to fit that outcome model.
So it would be you're just adjusting, you're fitting a different outcome model, essentially.
Yeah, in that case, it's part of that.
That was my
outcomes.
basically saying it's a fundamentally it's a propensity score misestimation. So you're like, if I just estimate, or it's the outcome piece though. Yeah, sorry.
Yes, you have to use the outcomes to fit that thing. There's no other way to do it. Yeah.
If I have a more flexible outcome model.
Yeah, exactly. And so the questions there are just sort of, I think the statistical theory questions are more like, where are those outcomes coming from? And I kind of alighted that in this talk.
Yeah, that clears that. That makes sense.
Okay, yeah.
Other questions, folks?
Yeah.
Back to your chart where you portray the mean.
Yes.
This is a very basic question, but why does one look why is one going that way and one going upside down?
Yeah, that's a really good question.
Why is the BBM model going in a different direction than the MSM model?
Yeah, to be honest, I don't have a really clear intuition for why this is happening, in particular for the MSM, because this is all just kind of numerical. I don't have a closed form for this relationship. One thing I will point out, though, is that these two scales are very different, right? On the y-axis, our design sensitivity is measured in terms of your sensitivity parameter, right? So in the BBM, you have a bounded sensitivity parameter that goes from 0 to 1. And so, design sensitivity can never be bigger than 1, no matter how big you make your effect, right? On the other hand, in the marginal sensitivity model, this is just a bound on a ratio, and it could be unboundedly large. And so my guess is that that's why we're seeing this shape, is that this curve eventually is going to have to fit underneath 1, whereas this one can get as big as it wants. So I think it's probably a question about parameterization and the different scales of those things. Great question.
Anything else? Probably have time for maybe one more question.
Yeah.
Yeah, first of all, thank you for sharing your ideas and details. It's really, really fantastic and really learned a lot. And my question is, your analysis show how to choose between augmentation and training, but I still have no idea how to choose between the variance-based model and marginal sensitivity model. It based on different contexts, but can you show more specific example of how to choose between these two?
Yeah. So I'll give. Yeah, I mean, to be honest, most of the examples I think of are reasons to use the variance-based model, because that's the paper I wrote, is about why to use that instead. So it's maybe this is a little bit of a biased example. But let's say you have some insight about your unobserved confounder, and you think your unobserved confounder is something that's normally distributed. So basically, most of the unobserved confounder values are going to be centered around some mean, but then you're going to get a few really extreme values. And let's also assume, I mean, you also kind of have to make assumptions about the way this unobserved confounder is going to enter into the formula for the weights. So, but maybe it's not crazy to believe that because you have this normally distributed unobserved confounder, most of the time it's going to be a relatively small shift to a weight up or down. But occasionally, for a few weights, it's going to have a massive, there's going to be some massive value of this unobserved confounder, and it's going to lead to a very, very different weight. So if that's what you believe your unobserved confounder behaves, it's definitely a better idea to use the variance-based model, because basically the marginal model is going to, you're going to have to choose this parameter entirely in terms of the worst difference in weights, whatever that is. Even if it only happens, less than 1% of the time, that's the error metric we have to work with. And so for that kind of unobserved confounder, maybe it's much more reasonable to think about the variance-based model, where you can kind of take an average case and yeah. So that's what I'd say.
What is the tree 0.9 and 1.8?
Yeah, this is what percentage of the observations we are trimming away. So we're getting rid of like the top 10% of observations. That isn't really like, I think if I were to make this plot over again, I might use a propensity score threshold instead, because that's probably the way these decisions are made. But this is kind of how is just to kind of take a quick stab at it. And I guess what's nice about this is, well, no, I think that's all the same. Yeah.
All right, well, we're at time, so let's thank Sam again for
Thank you.
and hope to see some of you at our next seminar, I think in a few weeks. So thanks again. Have a nice day, everybody.